Welcome to today's episode on the fascinating world of separation science. We'll be exploring the powerful technique of high-performance liquid chromatography, or HPLC, and its basics, working principles, and essential steps. So let's delve into the world of HPLC and discover how it aids in the detection and diagnosis of an array of illnesses and health issues. What is HPLC? HPLC is an analytical technique used to separate, identify, and quantify components in a mixture. The figure below shows a basic overview of the HPLC process. This powerful method is based on the principle of differential partitioning between a mobile phase, which is liquid, and a stationary phase, which is typically a solid packed into a column. Partitioning is the process by which molecules distribute themselves between two immiscible phases based on their affinity for each phase. The stationary phase refers to the substance that stays fixed inside the column. It is typically packed into the column and is designed to interact with the sample components in specific ways to cause differential migration and achieve separation. The nature of these interactions can be tailored by selecting appropriate stationary phases for the column, and these can include interactions such as absorption, partitioning, ion exchange, size exclusion, and affinity. The mobile phase is the liquid solvent that carries the sample through the system. It flows through the column and transports the components of the mixture being analyzed. The mobile phase is chosen to optimize the separation of the components of interest. Its properties, such as polarity and pH, affect how different molecules in the sample interact with the stationary phase, which in turn affects their separation. Now let's take a closer look at how HPLC works in detail. The process can be broken down into several steps. First is sample preparation. Before analysis, the sample may need to be prepared to ensure compatibility with the HPLC system. This can include processes such as filtration, dilution, or derivatization, depending on the nature of the sample and the specific HPLC method being used. For example, for blood samples, centrifugation separates plasma or serum from cells. High levels of proteins, which can interfere with HPLC analysis, are precipitated using organic solvents and removed by centrifugation or filtration. The supernatant is then filtered using a syringe or centrifugal filter with appropriate pore size for a clean HPLC injection sample. Next is sample injection. A small volume of the prepared samples introduced into the HPLC system using an injector or an autosampler. It is critical to maintain consistent injection volume to ensure accurate and reproducible results. To do that, we need to consider column dimensions, sample concentration, and the detector's linear range. For example, a common rule of thumb is to keep the sample injection volume below 1 to 5% of the column's void volume, which is the column volume minus the volume of the stationary phase, to prevent band broadening and maintain adequate separation. It is also important to use proper injection techniques to avoid air bubbles and confirm sample compatibility with the mobile phase. Next is the mobile phase. As we mentioned above, the mobile phase is a liquid solvent or a mixture of solvents. The mobile phase is continuously pumped through the system at a controlled flow rate and high pressure. Choosing the right mobile phase composition depends on several factors, such as chemistry of the analytes, the stationary phase, the separation mode, and the detector being used. Here are some examples of how to choose the mobile phase composition for different HPLC separation modes. If you were going to choose the mobile phase for reversed phase HPLC or RPHPLC, in which the stationary phase is nonpolar and the mobile phase is relatively polar. You can use a mobile phase consisting of a mixture of water with 0.1% trifluoroacetic acid, or TFA, and acetonitrile with 0.1% TFA, with a gradient increasing the acetonitrile content from 5% to 95% over 30 minutes. If you are going to choose the mobile phase for normal phase HPLC or NPHPLC, in which the stationary phase is polar and the mobile phase is nonpolar, You can use a mobile phase consisting of a mixture of hexane and isopropanol in a ratio of 95:5. Next is the column. The HPLC column is packed with a stationary phase, typically composed of small particles of a solid material or a porous polymer. The stationary phase is selected based on its chemical properties and the type of separation desired. As the sample moves through the column, its components interact with the stationary phase and are separated based on their affinity for the stationary phase and the mobile phase. Let's still take a look at normal phase and reversed phase HPLC. In normal phase HPLC, the stationary phase is polar, consisting of materials like silica gel or chemically bonded polar functional groups such as amino, cyano, or diol groups. In the normal phase, polar molecules elute slowly, and non-polar, greasy molecules elute quickly. On the other hand, RPHPLC employs a non-polar stationary phase, typically based on silica particles bonded with hydrophobic alkyl chains like C8 or C18 groups, where polar molecules elute quickly and non-polar greasy molecules elute more slowly. Next is separation. As mentioned above, components favoring the stationary phase stay longer in the column, while those preferring the mobile phase move quicker. Normal phase HPLC using a polar stationary phase separates via polar interactions, while reversed phase HPLC utilizes a non-polar stationary phase, separating analytes through hydrophobic interactions. Next is detection. After the components are separated, they elute from the columns and pass through a detector. The detector measures a property of the eluting components, such as their absorbance, fluorescence, or mass, and generates a signal proportional to their concentration. Common detectors in HPLC include UV visible absorbance detectors, fluorescence detectors, and mass spectrometers. And lastly is data analysis. The detector signal is collected and plotted as a function of time or volume, resulting in a chromatogram. The chromatogram displays peaks representing the separated components, with their retention times, peak areas, or peak heights being indicative of their identity and concentration. By comparing the retention times and peak properties to those of known standards, the components in the sample can be identified and quantified. Today, HPLC is an indispensable instrument in clinical diagnostics. In our upcoming video, we'll explore the utilization of HPLC to identify and measure diverse biomolecules and markers linked to illnesses and conditions. Stay tuned, and thank you for watching.